Hi everyone. We team 2468 Team Appreciate are here to present CANnections Made Easy. My name is Gracie Lee.
My name is Aarav.
My name is Arya.
I hope you have a great time.
So, what is CAN? CAN, or Controller Area Network, is how major robot components communicate with each other. Devices like the Robo-Rio, motor controllers, and the PDH or PDP will be connected on the same CAN bus. Instead of separate signal wires for each device, CAN uses a shared network. For this to work properly, termination resistors are needed at the ends of the bus, usually at the Robo-Rio and the PDH. All CAN devices must be on one continuous network, including motor controllers and sensors and gyros. If the network breaks at any point, communication can fail. Why is CAN important? CAN is important because communication is bidirectional. Unlike PWM, which only sends a voltage signal one way, CAN lets us send commands and receive status data back. This allows more advanced motor control, like velocity or position control, and lets motor controllers run their own PID loops. CAN also allows sensors to connect directly to motor controllers and reduces wiring, making the robot cleaner, more reliable, and easier to debug.
So let's go over some common CAN practices in FRC. So typically, CAN buses are daisy chained together, meaning they would start from the your power distribution hub or PDP and connect to the CAN of the neovortex or flex. And then that flex would have another CAN wire branching out to the next spark flex, and then that spark flex, and so on, would eventually lead to the rubber. The issue with this system is that if there's any disconnection between the devices or some malfunction that occurs during a match, then your entire system breaks. And your entire system breaking isn't great. So we want to reduce that risk. But before we tell you how we reduce that risk, let's go over an important detail that's related to that. It's star topology. So the philosophy behind star topology is that if you have all your devices connected to one single hub instead of to each other, they won't be so reliant on each other for continued communication. So if one device breaks, the others are fine. And as long as the hub is fine, everything will still be running. And it's just that one that's break. And the 2468 CAN bus, that solution, implements this hub system with a bunch of small star networks called starlets to which the devices connect to.
How does 2468 actually implement this? So what we do is we have custom CAN distribution boards or CDBs. These CDBs are act as our hub in the star topology network. And they're basically made up of Wago connectors. We used to use 250, 204 Wago connectors, but now we use 2601, 301, 3014 connectors. And we have two different versions of this, which you'll see on the next slide. We have the CDB4. This allows four pairs of CAN wires to connect to it. So two pairs to continue the chain, and then two pairs for other devices that are connected to it. And we also have a CDB8, which allows you to connect eight CAN pairs. And the star topology, it still kind of works like a daisy chain, but instead of relying on the devices to continue the daisy chain, which would be a problem if one device failed, we just use CDBs. So here are some pictures of what our CDBs look like. These are our old CDBs, which use the 250204, and these are our new ones. And as you can see, there's room for four pairs of CAN wires and eight pairs of CAN wires to connect to these.
So creating a layout like this is quick and highly effective for identifying potential issues and ensuring proper connections. So this allows for system reliability and quick maintenance. So for system reliability, if any drive or steer motor experiences a CAN disconnection, the rest of the system remains fully operational. And for quick maintenance, entire pods can be replaced quickly with just two disconnections from the CDB, ensuring the rest of the system continues to function without interruption. So for specific information on our CAN practices, so all CAN devices except for the RoboRio and the PDH or PDP connect to CDB only. Devices never connect directly between CDBs, which keeps the network organized and easier to manage. When we use Wago connectors instead of two-pin PWM connectors, we crimp ferrules onto the wire ends. This improves connection strength and reduces the chance of wires pulling out or loosening over time. One major advantage of this setup is reliability. Removing a device doesn't break the CAN bus because the network stays connected end to end through the CDBs. This makes repairs and swaps much faster during competition. This slide highlights a key physical constraint in our CAN network layout. Every CAN device has to be within 11 inches of its CDB connection. That limit is important because longer wire runs can introduce noise and reduce signal reliability. Our design team actually works with a stricter target of 9 inches. That buffer gives us room for clean routing, slack, and strain relief so the wiring stays compliant even after installation. Keeping these distances tight helps maintain consistent communication across the CAN bus and reduces potential troubleshooting issues later on. With that in mind, this guideline becomes the foundation for how we place and organize the rest of our components in the system.
So we have a special way we use JST connections. So usually, if you're doing the normal way of daisy chaining, which is chaining from device to device, then to connect to motor controllers, you have a JST wire, which has two CAN wires coming out of it, one to and one from. But we don't actually need to do that because we connect everything to a CDB. And as we mentioned earlier, everything connects to the CDB using ferrules. So what do we do about the JSTs? So JSTs, what we do is we put two wires into the middle of the JST, and then we have empty crimps of the JST, and we put them on the sides to make sure that it properly connects to the device. And so instead of having the normal way, which is two CAN wires coming to and from, we have one.
So how we accomplish swerve at 2468 is we have a 3D printed sort of platform that's mounted to the side of our rail, and on top we have spark maxes and a CDB. And our spark flexes and neos are modified in such a way that they only need one connection to this one pair of connections to the CDB. And so we plug them into the CDB. Then we have the two CAN wires coming from another CDB, and one coming from to another CDB. And the advantage of this is, of course, you can remove your pod really easily. But also, if we were using SDS, in case it is an added cost, we would need to get another CAN distribution board or a CDB8 to accommodate for that. So now we have a bit of a question for you as a viewer. So think back to something we mentioned before about our specific distance rules. Out of all of these things, what would pose a great problem? Well, those are elevators, of course. Since elevators are so long and change lengths, depending on how much they're extended, we've developed something called CAN over Ethernet. Instead of relying on CAN wire to continue the connection, we we transform it through Ethernet, which has extremely reliable shielding, and we plug it in. We plug in one at the bottom near the base, and then one attached to the top of the elevator. And that allows us to connect to any different devices on top of our elevator without sacrificing a lot of signal stability.
Okay, so how do we accommodate for this new system? How do we plan or wire a robot? Uh, So generally, for every robot, you have to kind of pre-plan the CAN network, especially with these new CDBs introduced. Um, that's one step. We'll go into that later. And the second one is, of course, before you do anything on the robot, you want to make sure all the components work. Because if you have a really easy problem that you could have fixed before wiring it, and you put it on the robot and you don't know what the problem is, that's going to make solving the problem so much longer. So a couple of things are updating firmware, like the Rev hardware client, assigning CAN IDs. This is especially important because if to keep track of them, because it allows you to see where everything is. So if a problem comes up, you'll know exactly where it starts. And if two electronics have the same ID, that causes major problems and stops your robot from working. So make sure you be on top of that. And another thing we'll get into is wiring the network really methodically. Um, we want to really emphasize this because, again, as I was saying, if you wire everything without testing it properly, then if you find a problem, you have to go all the way back and check everything again. So make sure that as you're doing it, you see where the problem starts. So here's kind of a step by step of how we do it. So we have like a kind of rough placement of our CDBs. Then we wire up basic parts of the CAN chain, like the rotary and the PDH. Then we check if they see each other. Then we wire up devices, and then we check if those devices work methodically and repeat for every single CDB.
So, going more into detail in this is the first step is testing the CDBs before they ever go on the robot. We use a small test setup, just like our briefcase system, to make sure each CDB works correctly. We also do a shake test to confirm the solder joints are solid and won't fall from vibration during a match. At the same time, we plan where all CAN devices will be mounted. This requires coordination between the electrical and design teams, so wiring routes make sense. Finally, we prioritize accessibility by leaving enough room for wires and hands, so and repairs are easy even after everything is wired. So step two is once all CAN devices are mounted, we start wiring the CAN network in a controlled order. Just like Arya mentioned, we need to test as we go. So first we connect the RoboRio to a CDB. Then we wire all the CDBs together in sequence, ending with a connection from the final CDB to the PDH or PDP. This ensures the CAN bus is continuous and properly terminated. At this stage, we don't connect any other devices to the CDBs yet. Keeping the network simple makes it much easier to test and troubleshoot before adding everything else.
So before we actually wire every device, we got to check that the basic components are working, the rotary and the PDH. So for that, we use Rev hardware client, and we basically see first from the PDH or first from the RoboRio if the PDH is visible, so that we can make sure that they can see each other, so no CDB or no component is not working. And then we go and plug in. Rev hardware client into the PDH so we can kind of backtrack and check from that side, which is kind of like a double check that verifies our connection between the two devices. And then lastly, the biggest part, which is connecting all the devices in a really methodical process. So for every CDB from the RoboRio to the PDH, we plug in our devices and then we check using Rev hardware client if a CDB can see those devices. So you can see the devices and you can see the PDH and the RoboRio. So everything needs to be online. And basically, we go through that for all our motor controllers and sensors on our CDBs. And we go through every CDB until we can be sure that all CAN devices are seen on the PDH and RoboRio.
So we draw our canvas using KiCad's schematic capture tool. So we created these symbols for our different components in KiCad, and now we draw three schematics for our robots, all CAN connections and then all power connections, and then Ethernet sensors and everything else. So these will be three separate schematics, and they'll eventually like kind of come together when we actually wire the robot. So this is our last year's, or sorry, 2 years ago, 2468 robot CAN map.
So, uh, we talked about CDBs earlier, and we just want to share how you can get your CDBs. So, first of all, we have a Google Drive here, which we can post in a link under this video, with the Gerbers associated, and you can buy it and commission it yourself. But before we do that, we just want to give a simple price breakdown based on recent events. So, currently, taxes, shipping, customs duties are quite high compared to the years before. So this option may not be viable for you. For example, you see here, when we buy the board from PCBWay, they need to ship it overseas. So you have this great cost here of $24.53, when before it was just before all those taxes, you see it was only $16.90 for 50 of the boards. And the Wago connectors themselves are fairly expensive if you want. So it would be around two for each board if you had a CDV4. And those are around $2.35 per pair per. So if you were to assemble 50, then you would need 100, and that would get you to around $240. And in total, you have around $242.75 per board. And you might want to consider how you might justify this cost and if you believe that it's good for your team. And yeah, that's it. Thank you guys for listening. If you have any questions, please email us, talk to us, and check out all our other presentations on YouTube. We have some great ones about scouting across our three teams, time management, and batteries, intros to PID, and personal projects. We highly suggest the Battery 101 because it's a part of our electrical sub-team, so please support them. Thank you so much. Happy kickoff.
Happy kickoff.
Happy gig.